In mathematics, the discrete-time Fourier transform is a form of Fourier analysis that is applicable to the uniformly spaced samples of a continuous function. The term discrete time refers to the fact that the transform operates on discrete data whose interval often has units of time. From only the samples, it produces a function of frequency that is a periodic summation of the continuous Fourier transform of the original continuous function. Under certain theoretical conditions, described by the sampling theorem, the original continuous function can be recovered perfectly from the DTFT and thus from the original discrete samples. The DTFT itself is a continuous function of frequency, but discrete samples of it can be readily calculated via the discrete Fourier transform, which is by far the most common method of modern Fourier analysis. Both transforms are invertible. The inverse DTFT is the original sample data sequence. The inverse DFT is a periodic summation of the original sequence. The fast Fourier transform is an algorithm for computing one cycle of the DFT, and its inverse produces one cycle of the inverse DFT. Definition: the discrete-time Fourier transform of a discrete set of real or complex numbers, x, n, for all integers n, is a Fourier series, which produces a periodic function of a frequency variable. When the frequency variable, I per mil, has normalized units of radian sample, the periodicity is 2I euro, and the Fourier series is. The utility of this frequency domain function is rooted in the Poisson summation formula. Let x, f, be the Fourier transform of any function, x, t, whose samples at some interval, t, are equal the x, n, sequence, that is. Then the periodic function represented by the Fourier series is a periodic summation of x, f. In terms of frequency in Hertz, the integer k has units of cycles sample, and 1 per ton is the sample rate, fs. So x1 per ton, f, comprises exact copies of x, f, that are shifted by multiples of fs Hertz and combined by addition. For sufficiently large fs the k equals 0 term can be observed in the region, and fs/2, fs/2, with little or no distortion from the other terms. In Fig. 1, the extremities of the distribution in the upper left corner are masked by aliasing in the periodic summation. We also note that as the Fourier transform of therefore, an alternative definition of DTFT is. The modulated Dirac-Comb function is a mathematical abstraction sometimes referred to as impulse sampling. Periodic data, when the input data sequence x, n, is n-periodic, EC2 can be computationally reduced to a discrete Fourier transform, because all the available information is contained within n samples. Converges to 0 everywhere except integer multiples of known as harmonic frequencies. The DTFT is periodic, so the maximum number of unique harmonic amplitudes is, the kernel is n-periodic at the harmonic frequencies, so is an infinite summation of repetitious values, which does not converge for one or more values of k. But because of periodicity, we can reduce the limits of summation to any sequence of length n, without losing any information. The result is just a DFT. In order to interpret the DFT, it is helpful to expand the Comb function, from EC3, which is now NT-periodic, into a Fourier series. Which also shows that periodicity in the time domain causes the DTFT to become discontinuous and that it diverges at the harmonic frequencies. But the Fourier series coefficients that modulate the comb are finite, and the standard integral formula conveniently reduces to a DFT, which is an n-periodic sequence that completely describes the DTFT. Inverse transform, an operation that recovers the discrete data sequence from the DTFT function, is called an inverse DTFT. For instance, the inverse continuous Fourier transform of both sides of EC3 produces the sequence in the form of a modulated Dirac-Comb function. However, noting that x1 per ton, f, is periodic, all the necessary information is contained within any interval of length 1 per ton. In both EC1 and EC2, the summations over n are a Fourier series, with coefficients x, n. The standard formulas for the Fourier coefficients are also the inverse transforms. Sampling the DTFT. When the DTFT is continuous, a common practice is to compute an arbitrary number of samples of one cycle of the periodic function x1 per ton, where xn is a periodic summation. The xn sequence is the inverse DFT. Thus, our sampling of the DTFT causes the inverse transform to become periodic. In order to evaluate one cycle of xn numerically, we require a finite length x, n, sequence. For instance, a long sequence might be truncated by a window function of length L, resulting in two cases worthy of special mention, LA per mil currency n and L equals E a euro cent n, for some integer I. For notational simplicity, consider the x, n, values below to represent the modified values. When L equals E a euro cent n, a cycle of xn reduces to a summation of I blocks of length n. This goes by various names, such as multi-block windowing, and window prism DFT. A good way to understand motivate the technique is to recall that decimation of sampled data in one domain produces aliasing in the other, and vice versa. The xn summation is mathematically equivalent to aliasing, leading to decimation in frequency, leaving only DTFT samples least affected by spectral leakage. That is usually a priority when implementing an FFT filter bank. With a conventional window function of length L, scalloping loss would be unacceptable. So multi-block windows are created using FIR filter design tools. Their frequency profile is flat at the highest point and falls off quickly at the midpoint between the remaining DTFT samples. The larger the value of parameter I, the better the potential performance. We note that the same results can be obtained by computing and decimating an L-length DFT, but that is not computationally efficient. When LA per mil currency n, the DFT is usually written in this more familiar form. In order to take advantage of a fast Fourier transform algorithm for computing the DFT, the summation is usually performed over all n terms, even though NL of them are zeros. Therefore, the case L